In this video, we're going to cover section 5.7, which is the last section that we will do out of chapter 5 on differential equations. So the objectives for this section: determine general and particular solutions of a differential equation, verify that a function is a solution of a differential equation, solve differential equations using the method called separation of variables, and solving applied problems using the separation of variable method. All right, so the definition: a differential equation is an equation that includes a derivative. So any equation that has a derivative in it and has a function as a solution. So it's not just a number, right, but the solution to it represents a function for which the derivative is given within the equation. All right, solving certain differential equations. All right, so it depends on the type we're solving as to how that process works. We actually find solutions of certain differential equations when we find their antiderivatives or indefinite integrals. Okay, so we've already done this general process already. We just haven't called it this yet. All right, example 1. Solve y prime, or the derivative of y, equals 2x. All right, so we already talked about that when we work backwards and find an antiderivative. Right, that is the process of solving an equation like this. So if we're given the derivative, y prime equals 2x, to find the function y, right, that's what we're looking for, we take the antiderivative of the derivative. That works backwards. So the antiderivative, just the indefinite integral of 2x, would be x squared. And then remember, we add the plus c at the end. This is called the general solution. In other words, we're looking for the function whose derivative is 2x. C can be any constant because the constant derivative would be 0. All right, let's try another one. This time we are given to solve, again, y prime or f prime of x is given to be this function, and we're given that f of 0 equals 8. So when we did these before, we didn't call them differential equations, but that's what actually they are. F of 0 equals 8 is information that's going to allow you to solve for c. Okay, so we're going to do this the same way we had done it in the past. The general solution to get back to f, if I'm given f prime, to get back to f, we take the antiderivative of the f prime. So the antiderivative of this function that we were given. So the antiderivative of e to the x is itself. Here the antiderivative, 5 would stay in front. You get x squared over 2. Here you're going to add 1, so a half plus 1 is 3 halves. Divide by 3 halves is multiplied by 2/3, and then we put the plus c at the end. Okay, now we're going to substitute the 0, 8 that we were given. Remember, let me back up here real quick. We were given f of 0 equals 8, so that's the ordered pair 0, 8. So we're going to substitute x is 0, y is 8 to find our c. Right, so that was our antiderivative. So this side was y, so we plug in the 8. This is the x was here, and here we're plugging in 0 for all those x's. So this is just 0, this is 0, but e to the 0 is 1. So this is a 1, and then those are 0 plus the c equals 8, which means the c equals 7. So then we're going to take that, and this is called the particular solution when you plug that number back in for c. So back to our y equals or f of x equals, right? We got this as our answer, and then put in your value for the c. So the general solution is when you just add the plus c. The particular solution is what we call it when we actually solve for the value of c. All right, here we're going to verify. We're going to show that this function is a solution to this differential equation. This is a differential equation because it contains derivatives. It contains the second derivative of y and the first derivative of y and y. So the derivatives are contained here. That's why it's called a differential equation. And we're given the answer. We're just going to verify it. All right, so we're going to plug it in. So we know what y is, so we can plug in y here, but we also need to find the first and second derivatives, so we can plug them in here and here. All right, so y prime would be, take the derivative of this function, 4, derivative of e to the x is itself, 5 would stay in front, derivative of e to the 3x is e to the 3x again times 3, so that e to the 3x times 3 makes this coefficient 15. So we get That was our first derivative. Now again, for the second derivative, again, this derivative would just be itself. Here we'll multiply again by that 3, making the new coefficient 45, so e to the 3x times the 45. Then we're going to substitute. So that was our given differential equation. So this is what we got for y double prime, minus 4 times what we got for y prime, plus 3 from here times what we were given for y, equals 0. So here they've just cleaned this up. So this thing distributing the negative 4 through here, distributing the 3 through here. And then notice if you combine like terms, 4e to the x minus 16e to the x, that's negative 12e to the x plus 12e to the x, that's a 0. 45e to the 3x minus 60e to the 3x, that's negative 15e to the 3x, but then plus 15e to the 3x is also 0. So all these, if you combine like terms, they cancel, and you get 0, and that was supposed to equal 0, which means that we verified. Right? Since a true equation results, we know that that would be a solution. All right, let's try one more. Show that y equals x squared plus x is a solution of this differential equation. So here we just need the first derivative because we're given what y is, right? We just need to know what y prime is. So we're going to find the first derivative. Y prime would be 2x plus 1. Now we're going to substitute. So we substitute 2x plus 1. Right, they're just rewriting it first. So we're going to plug in our 2x plus 1 for y prime, plus the 1 over x would stay. This was y. We were given that. Equals, we put a little question mark because we're going to check to see if they're equal, and then the other side doesn't have a y, so it stays as 3x plus 2. So the 2x plus 1 stays here. We're going to distribute 1 over x through the parentheses. So 1 over x times x squared is just x. That's this x right here. Plus, and then 1 over x times x is the 1. And then on the left side, if I combine like terms, I get 3x plus 2, and that's what it was supposed to equal, right? So that is verified. Since a true equation results, we know that our y equals x squared plus x is a solution. All right, so now we're going to try to talk about how to solve using method of separation of variables. So the first few examples that we solved, all we had to do was find the antiderivative. Right, it's not always going to be that easy. Sometimes differential equations are not written in that form, but this is the first basic method on how to solve. If you ever take a course called Differential Equations, you'll learn lots of other ways to solve. Because again, this won't always work, but for what we're going to learn, this is the only method that you'll have to know how to do. All right, so we say that a separable differential equation is a differential equation if it's possible to write it in this form, meaning rearranging it to where all the y's are on one side and all the x's are on the other side. All right, so if you think about the initial equation would have had to involve a derivative, meaning a y prime term. So what we would have to do to write it in this form is think of y prime as dy over dx and then start moving the dx and the dy around to get it to look like this right here. All right, so here, let's try to solve 3y squared dy over dx, which is y prime. They've just already written it in that form for us, plus x equals 0, where y equals 5 when x equals 0. So we're going to wait for this stuff until a little bit later toward the end because we'll have to solve for our c with that, okay? So we'll come back to needing this stuff after we've done our separation process. All right, so first we separate the variables. Okay, so the first thing that we do here, all this stuff's being multiplied, so they just move the x to the other side. So that's negative x on if I subtract x from both sides. Then taking this side and multiplying it by dx cancels the dx here, leaving just 3y squared dy. But then I got to multiply by the dx on the right also. So multiplying both sides by dx. Notice we've separated. Only y's on the right, only x's on the left. Okay. Now we integrate or take the antiderivative of both sides. Okay, so we had 3y squared dy equals negative x dx. We just put an antiderivative symbol in front of both sides. So the antiderivative of 3y squared The 3 would stay. You get y cubed over 3, which would cancel that 3, leaving just y cubed, equals, negative stays in the front, x squared over 2, and then we'll put the plus c. Technically, there's a plus c1 and a plus c2 on both sides, but then if you moved all constants to one side, we can just write it down as one constant. So we'll only add the plus c on one side. All right, here all they've done is just rearrange this and put the c in the front, minus x squared over 2 behind it, just because you can. Okay, and then we're trying to solve for y, remember, so to get y by itself, we have to cube root both sides, so the cubed root on the right. So that's a general solution. Remember, they gave us values for x and y, right? So they said x equals 0 when y equals 5, or y equals 5 when x equals 0, so we're going to plug those in and solve for c. So we plug in y equals 5 and the x value for 0 into that previous step that we had. So this is just 0. So the right side becomes the cube root of c equals 5, and then you cube both sides to get rid of the cube root. So 5 cubed is 125 equals c. So the particular solution would be that general solution we got with the 125 plugged in for the c. Okay. All right, so let's try another one. Solve 2 square root of y dy over dx minus 3x equals 0, where y is 9 when x is 0. All right, so start by separating. All right, so there's what we were given to start with. First thing we're going to do is add 3x to both sides. Now we're going to multiply both sides by dx. Now we're going to take the antiderivative of both sides. Okay, so the left side, remember, square root of y means y to the 1/2. So when I'm doing the antiderivative, I add 1 to a half, I get 3/2. And when I divide by 3/2, I'm really multiplying by 2/3. So that's where the 4/3 comes from. Equals, here the 3 would stay, you get x squared divided by 2, and then plus your c. All right, so again, we want to solve for y, so we're going to multiply by 3/4. That would leave this. So this right side is going to get multiplied by the 3/4. All right. So what they've done here, they've distributed the 3/4 in. So 3 times 3 is 9. 4 times 2 is 8. X to the 1/2. 3/4 times c is just a different c, right? It's still a constant. So they just left it as a c. And then raise both sides to the 2/3 power, right, to make this fraction exponent become a 1. So if I raise this side to the 2/3, right, that becomes just y. That means I have to raise this side to the 2/3. All right, now we're going to substitute 0 for x and 9 for y. So here was the x, here was the y. We're going to solve for our constant. All right, so here, this part is 0, leaving just the c. So it would be c to the 2/3. So again, to solve, you got to raise it to the 3/2 power to make that power a 1. So that means this side gets raised to the 3/2 power. And 9 to the 3/2 is 27, because calculator could do that for you, but this really means the square root of 9, which is 3, then cubed. So 3 cubed, right? That's where the 27 comes from. And then we plug that back in to our answer, and then that is our particular solution. All right, so let's try another one. dy over dx equals x over y. All right, so again, we're going to start by separating variables. Y would equal, so the first thing it looks like they did here is multiply both sides by y. Okay, so times y here cancels, it leaves x on the right, and you times the other side by y. Then they multiplied by the dx. It doesn't really matter the order in which you move things around as long as you get to that point. Y dy equals x dx. You could have done that also by just cross multiplying at the very beginning, would have gotten you the same result. All right, now we're going to take the antiderivative of both sides. going to give me y squared over 2 equals x squared over 2 plus c. So we're going to multiply everything by 2 to clear the fraction. So y squared equals x squared plus 2c. So everything gets multiplied by 2. And notice here, okay, so they square rooted to get rid of the power 2. So that's where the square rooting this side is plus or minus the square root. And they just relabeled 2 times c to be a different constant, c1. You don't have to do that necessarily, but it just cleans it up a little bit. So that c1 is the same as the 2c. They just replaced 2c with a different constant, c1. And it just makes it look a little bit nicer. All right, by the way, there was no initial condition here, so that's just the answer, right? We weren't given information to solve for c. So when you're not given information to solve for c, you can't. You just have to leave that in your answer. All right, so if you want to try this one on your own, you can. I would remind you here, we didn't see one like this yet. The first thing I would do is write y prime as dy over dx. And then you can try and see if you can get it separated and solved. All right, so we start with this. So they've rewritten this as dy over dx, and they've divided both sides by y. Okay, so this just changed to this notation, dy over dx, and then they brought the y to the other side by dividing both sides by the y. Then they multiplied both sides by the dx. So they'd left the 1 over y and the dy here, times dx would cancel it, and it would also multiply on the other side, giving you x squared dx. Now we're going to integrate both sides. Take the antiderivative of the left and the right. So the antiderivative of 1 over y is natural log of y. The antiderivative of x squared would be x cubed over 3 plus the c. So here to solve for y, because there's a log, you have to use e. So think of this as this left side making this the power of e. So e to this power is just y. So the same thing on the other, e to this power. This becomes the exponent on e. Then they do some simplifying from here. So just using exponent rules, e to this power is the same as writing e to the x cubed over 3 times e to the c. The reason you know that is if you had like bases that were multiplied, you would simplify by adding the exponents. So they're just doing that in reverse. So e to this power times e to the c power. And because e is a constant and c is a constant, e to that power c is just a different constant. So kind of like the last one, they clean that up a little bit. So e to the c is just renamed as c1 times e to the x cubed over 3. That's a common practice when solving a differential equation, is to kind of clean up the answer than if it still involves your constant. And here they're just explaining that step, right? Since that is an arbitrary constant, they replaced it with just a new constant and relabeled it as C1. All right, so here is our summary for this section. A differential equation is an equation that includes a derivative and has a function as a solution. A general solution of a differential equation of the form y prime equals f of x is the set of functions y equals the antiderivative plus c, where the derivative of the capital F, right, will get you back to f. And that's how we had seen those before. For many differential equations, the general solution is of the form y equals c times a function where c is some constant. A requirement that a solution of a differential equation include a specific ordered pair is called an initial condition. That's the condition that allows you to solve for the constant. If an initial condition is given, then a particular solution in which the value of c is determined can be found. So when you're given the initial condition, you're finding the value of c, that's called a particular solution. When you're not given initial conditions and there's still a c involved in your answer, that's called a general solution. Okay, a separable differential equation is an equation in which the variables can be separated to opposite sides of the equal sign in the form f of y dy equals g of x dx. So the y is on one side, x is on the other. And then to solve a separable differential equation, the variables are separated. Then you take the antiderivative by integrating both sides. And if possible, you then solve that equation for y. They say solve for one of the variables, but typically we're looking for y. So we want to be solving for y. All right, so that then is the end of section 5.7 and the end of chapter 5.